Okay, so what's the maximum acceleration a car can undergo if the coefficient of static friction between the tires and the ground is 1.2? All right, this is the only thing you know is the static friction. All right, so what's the maximum acceleration that it can undergo? Oh, this is cute. That is the problem. Okay, so how do you do a problem like this? Okay, this sort of stuff requires a little bit of that's the reason why it's 6 for Planet. The first thing I'm going to do is just put everything on the coordinate system. All right, this is going to help me think when I'm doing it. All right, so you got the X and the Y coordinate system. The next thing I'm going to do, I'm going to do, all right, so the static frictional force is going to apply a force on the ground. The ground is going to apply a forward force on it. All right, so there's going to be a force acting in this direction. It's going to cause it to accelerate. So this is the force, okay, which is going to come from the static frictional force. All right, remember through friction, you apply a force on the ground in the backward direction, and the ground is going to apply the same force back on you in the forward direction. All right, so this is going to be mu sub s times n. And so I know that there's going to be weight acting on it. So this car is on a surface, so which means that there's going to be a normal force acting on it. Okay, so all of a sudden I'm thinking I don't like this expression, just keep it like that. All right, I'm good now. Okay, so the static frictional force acting on it is going to be the same force that the car is applying on the surface, on the ground, in the backward direction. So ground is going to apply the same force on the vehicle in the forward direction. Okay, cool. I got everything I need. All right, so how do we do this problem? Boom, acceleration is what I want. Okay, here's the formula. This is the net force. It is the net force. So net force on the x direction is the static frictional force acting in the forward direction. It's going to be responsible for the acceleration. All right, so active portion of the formula is right here. Okay, so get rid of the mass. Okay, so let's check to see what we got. Mass, I don't have. Okay, that's an unknown. Static frictional force. I don't have the static frictional force, but I know I have this, mu sub s. For me to be able to get to static frictional force, I need to know what n is. All right, so that's what I'm going to go after. All right, so which means that this is, okay, I killed it. Okay, so this is what I'm going to go after. Static frictional force, mu sub s times n. I can get n from the fact that n is a reaction force to the weight. So look at the net force on the x, y direction. N is up, w is down. And guess what? There's no acceleration. N is the same as w. W is the same as mg. All right, back substitution. So you got mu sub s times mg. Back substitution. So the acceleration is mu sub s times m times g. Masses are the same, so they will cancel. They're not, so the mass doesn't matter. That's what it means. Final equation, mu sub s times g. That's it. There's nothing else left. All right, so plug the numbers in, and then you're done. Okay, so this was
meters per second squared.
Say it again.
12 meters per second squared. Then.
Man, this is, give yourself 5 points for that one. This is actually more than the acceleration due to gravity. That's actually interesting. This is the maximum acceleration that this vehicle can undergo if the engine can handle it. Yeah, this is awesome. Okay, this is also, do you guys notice how little information is given? Okay, literally the only information given to you here is, here's the coefficient of friction. You don't know what the mass of the car is. You don't know if it's a fourth temper or a bus or a motorcycle or a bicycle. It doesn't matter. The only thing you know is the coefficient of friction. So what's the maximum acceleration that it can undergo? You know, you got all these formulas with accelerations in them, but the only formula that matters is this one. Okay, guys, acceleration is caused by the net force. And you need to interpret the net force as the net force. I could have put the subscripts here, but it's fairly obvious that the motion is along the x direction. So the action force is acting on the ground in the opposite direction. That's the static frictional force. The reaction force is acting on the vehicle in the forward direction. Once again, it is the same as the static frictional force. Okay, notice there's a conceptual element to this problem solving. This is highly realistic because, and you can't really break this down into 5 different steps to solve it because of the simple reason that you got only one single number given. You don't have the mass, you don't have the n, all right, so you cannot get the weight. The only thing left to do is the substitution. All right, so understanding of the concepts. Net force is the static frictional force. Static frictional force is a combination of coefficient of friction and the normal force. Normal force is a reaction force. Look at the net force acting on it, which is acceleration to 0. So you get the same value, and then back substitution and back substitution, and it just works out. All right. Okay, guys, let's go. 640. Okay, so let's do a quick review. Quick review. All right, so the external force, whenever we walk, where does it come from? We get the external force from where?
The ground.
Yeah, hold on, don't say anything else. Okay, cool, because it was muted. Okay, cool. So where do we get the external force from?
The ground.
Okay, so I need more. Okay, so where do we get the external force from? We get it from somewhere. Okay, guys, whenever we walk, the external force comes from friction, right? So you apply a force on the ground, or more like parallel to the ground, in the backward direction. So that becomes your action force. In turn, the ground applies the same force back on you in the forward direction. So that becomes the reaction force. Okay, so action and reaction forces through friction. Okay, question number 2. Which car is going to come to a stop sooner? The one with or without the anti-lock brake system?
With anti-lock brake system.
Very good. Give yourself 5 points for that one. The one with the anti-lock brake system will come to a stop sooner because?
Well, because it'll hit the static point. It'll hit the static and then drops the kinetic and then bounce back up to the static. And kinetic is constantly keeping itself averaged in a better place than just letting the tires roll.
Okay, I'll give you 5 points. This one is I have to find the right wording on this one.
And also is hitting the brakes about 18 times per second, I believe.
It does. Give yourself 5 points for that one. Okay, anti-lock brake systems will lock up the brakes or pump the brakes 18 times per second while increasing the average static friction force, right? Okay, an average static frictional force is going to be larger than the sliding friction. Okay, so that's the reason why it's going to come to a stop sooner. So anti-lock brake system is going to lock up the brakes or pump the brakes 18 times per second, and that's going to increase the average static frictional force. So the average static frictional force goes up. All right, so what's happening is, here's the force. You lock up the brakes, so the static frictional force is going to become maximized. As soon as it's maximized, the car is going to go into a skid. All right, so it's going to give you kinetic friction. And this one is your static friction. This one is the maximum static frictional force. Okay, so let's just go across. So what does the anti-lock brake system do? The anti-lock brake system is going to lock up the brakes 18 times per second. So within this region, this is the only region which is higher. Notice that faster this locks up, smaller this region becomes. As a result, the average static frictional force is going to be larger. All right, so here's your average static frictional force. Your average static frictional force is going to be larger than kinetic friction. That's it. Okay, so what are the contributing factors to surface friction? Okay, commonsensically, you can come up with 3, right? Okay, what are those? You can say the surface area,
Weight, the coefficient, and the surface area.
That's it. Give yourself 5 points. Commonsensically, you can say it's the surface area, it's the coefficient of friction, which is the nature of surface, and lastly, the apparent weight, right? Okay, so the next question is, how much does the surface area contact? How much does the surface area contact contribute to surface friction?
None.
Very little.
It's going to be none, you could say, or very little. Very little is more like, for smooth surfaces, it's none. Very little if it's rubber on concrete. It's so little, in fact, that it's negligible, or it's ignorable. Okay, so what are the static and kinetic frictional forces, and how do they differ? So static means it's stationary. Kinetic means It's sliding, right? Okay, so how do they differ? The only thing you need to know is the maximum static frictional force is going to be larger than kinetic friction. Okay, so maximum static frictional force, like it's right at the edge of sliding, is the maximum static frictional force. When it's maximized, it's literally, if you maximize it, it's gonna go into a skid. It's gonna go into a slide. So near the maximum value, it's gonna be larger than kinetic frictional force. Okay, just like here, near the maximum value, this region is larger than the kinetic frictional force. All right, so how do they differ? They differ in a sense that the coefficients of friction is gonna be different. All right, so they will have different values. It's the static case, rubber on concrete. Ooh, it's, what is it? The rubber on concrete book we're using for that one. I think it's 1.2. And as soon as it goes kinetic, it's going to 0.85. Okay, so the traction numbers are different. All right, so which one is larger? I think I need to move this down. Static friction is going to be larger. So the static frictional force is going to be larger. Okay, so I move things around. The question is why? Because the static frictional force right at the verge of skidding, the traction is going to be a lot more. And then what happens? The traction diminishes. So that's the reason why. A lot more traction at the verge of skidding. And as soon as it starts to skid, it's going to become larger. All right, so that's the reason why. Okay, so the next question is the anti-lock brake systems. They lock up 18 times per second. So the question is why? They lock up 18 times per second because more often you lock it up. Okay, when 10 times per second, you cover this region. 15 times per second, notice that this region gets smaller. 18 times per second, this region becomes smaller. So it locks up 18 times per second in order to increase the average static frictional force. So 18 times per second in order to increase the average static frictional force. So that's the whole idea. So you lock them up 18 times per second in order to increase the average static frictional force. Okay, so if you don't have anti-lock brakes, why is it recommended? Why is it recommended that you do with the brake pedal while the car is skidding? Okay, so if you don't have the anti-lock brake system, instead of locking up the brakes, what's the best thing to do or better thing to do? I don't know if it's the best thing to do, but usually that's a better thing to do. It's to pump the brakes, right? Just pump the brakes. Okay. The problem with pump the brakes, I wonder what the data on that is. Okay, I mean, obviously this stuff that we get says pump the brakes. Guys, notice that when you pump the brakes, oh, okay, so it goes into a skid and then you let it go and then you lock up the brakes and then it goes into a skid. You lock up the brakes. Ooh, only this region is higher than this one. I wonder, just pump the brakes once per second is going to make that much of a difference. I want to see the data on that. So